Tactile feedback to someone's real hand while they see someone stroking an artificial hand. You can actually measure by the level of someone's response to a noxious stimuli, whether or not they have actually obtained that embodiment. And one thing I'll just put out is I don't think we have great ways of measuring embodiment other than this kind of roundabout measure. So that's something I think our community could do better. But getting into this embodiment and how we might be able to do this for haptics, is that we started with traditional kinesthetic feedback devices like the ones that Usama talked about and like those that are attached to something like the Da Vinci surgical system. But what I'd like to do for mobility is to get away from these large, relatively expensive desktop or ground-mounted haptic devices. Thank you. And so what happens left if we get rid of kinesthetic or force-based feedback? Well, we have cutaneous perception, right? Measuring, providing feedback to the skin. So this video is a set of videos is an oldie but goodie from, as you can tell by the dress and the style, from the late 70s, early 80s. And it's this famous work where they show that, you know, someone who has all of their faculties about them can easily grab a match and strike it. However, if they've had local anesthesia just to dull their tactile sense, but they still have all of their dexterity, all of their visual perception, all of their sort of proprioceptive and kinesthetic feedback, just losing the tactile sensation on the skin makes it extremely difficult to pick up a match. And this also is a good reason that robots without tactile sensing have a lot of difficulty doing fine manipulation tasks. So eventually she gets it, but only after doing a power grasp on this little match. And of course, it takes a lot longer. So this highlights the importance of cutaneous or tactile sensing and feedback. And it is, however, a very complicated sense in order to stimulate, because you have a lot of different mechanoreceptors embedded in the skin. Depends where on the body you're talking about, what sorts of mechanoreceptors are available. And then also each mechanoreceptor has a different sort of type of response. It responds to different stimuli, responds to different frequency ranges. And so it is difficult to build stimuli devices, especially those that are wearable, that can be able to stimulate all of these different mechanoreceptors. So we don't necessarily try to do that, but we have to pick and choose what sort of stimuli is important for different types of scenarios. So if we want to truly take advantage of cutaneous stimuli, this might be one way to do it. So this is a weird little device that we built a while back based on soft robotics. And basically it uses this technique of particle jamming, where you take something like silicone rubber, you fill it with a particle or granular material, like in this case, coffee grounds. You can vacuum the air out and change its mechanical properties. And this is an interesting way of providing a haptic device that truly gives kinesthetic plus tactile experience. But the way that it does that is super brute force. All we're trying to do with a system like this is create a digital clay that recreates the physical world that you want to display. And so while that is maybe a compelling idea, in practice, it's super hard, and it ignores something that we've been trying to do in the haptics field for decades, which is to create haptic illusions, make people feel more than what the hardware can actually do. This is too literal of an approach if we want to provide mobile haptic feedback. And as you can still see, it's not really something you're going to mount on your body or hand. So what can we do that's mobile? Well, it's well known that you can use vibration feedback. John alluded to vibration feedback as well as a great modality. And it is great for many reasons, because when you feel vibrations, our mechanoreceptors that respond to high frequencies are very sensitive. It's super salient. It draws your attention. But a lot of vibrations really occur as an information about an event. It sort of tells you that something is happening, but not necessarily the details. There's not a lot of information throughput, even if there's a lot of attention that can be drawn to it. So this is just an example of a vibration project where we're trying to go beyond just vibrations calling your attention to something, but actually having meaning. So rather than just displaying a sinusoid, you can do something like hit the vibration hard in one direction and then recover and have lower skin deformation in a different direction. And it turns out this can give people the sense that they're being tugged in a particular direction. And there's some other really interesting ongoing work that's more tied to the neuroscience community about how these types of asymmetric vibrations not only feel like a tug, but they make people compelled to move in a particular way, which is different from just receiving feedback. But that, I'd say, is still an open scientific problem, why people respond that way, and how do you make this really work. Also, as I have blown past the age of 50, as you get older, I'm discovering that these haptic illusions work not as well. And so I joke to my students, I'm like a chef that's losing her sense of taste. I'm a haptician that as I age, as we all age, actually lose our tactile acuity, and some of these illusions don't work as well. So that's another challenge for us. So if vibrations are not the best way to do it because they're more about events, and it's difficult to really display realistic scenarios. Another way to do it is through fingertip skin deformation that is more DC or quasi-static. And this idea was really brought forth by Domenico Praticizzo's group in Italy, which he called sensory subtraction. So the idea is when you interact with the world, you have all this cutaneous and kinesthetic components, and if you take away the kinesthetic part and all you have left is skin stimulation, that sensory subtraction still works pretty well. And so a lot of different groups have worked on different devices to enable this. And this is one example from our research lab. And this video here shows really well how this skin deformation works. There's nothing that's preventing my student from, pushing right past this virtual block, but the local skin stimulation is sufficiently realistic to cause him to do the right thing when he manipulates these virtual objects. So for example, if you squeeze a virtual object, there's nothing that prevents your fingers from passing through each other. However, just feeling that skin stimulation is sufficiently realistic such that you can recognize objects and also object properties. So briefly, I'll also give a push for anyone thinking about doing haptics research or asking about realism, that I feel like our field has gotten really focused on psychophysics. So providing types of experiments where we ask people, here's a stimulus, which one is stronger, A or B? And we'll say something like, this stimulus is representing mass of an object. And what I've realized in recent years is that when we ask subjects in our experiments questions like that, we're already telling them that it's mass. And they might do a great job of identifying different intensities, but it doesn't tell us that what they're actually feeling is that mechanical property. So this is an example of a kind of open response paradigm type of experiment that I'm really pushing my students to do now, which is rather than telling students, here we have mass A and mass B, which one is heavier, now we provide different stimuli, masses, virtual masses of two different of weights, and then we say, what's different between them? Subject, tell me that, rather than which one's heavier. And then we can sort of see where people get confused, where the haptic illusion is working, and where people are actually responding in a naturalistic way to our stimuli. And so this is just a one visualization where we presented with subjects with mass, stiffness, and friction coefficient differences in objects, but we didn't tell the subjects what it is that was different. We just said, manipulate these virtual objects and tell me what you feel. And so most people could recognize that when there was a change in mass, it was indeed mass. So the thickness of these lines says how many subjects responded that way. Interestingly, people get really confused with stiffness. And then with friction, people actually do a pretty good job. And so you might look at this and say, this sort of stimulus is not great at stiffness display. And then we went back and we did the first ever experiment like this with real world objects. And it turned out that people responded the same way. And so we can't really hold our haptic devices to higher levels of performance than what humans can do with real world objects, unless we have a different kind of goal. If our goal is realism, this is probably the best that we can do. So this effect with this skin deformation feedback with no kinesthetic feedback only works well for relatively lightweight, low force objects. So it works well for dexterous manipulation tasks, surgery, where if you're doing a good job, you're not applying very high forces and such. So I do believe still if you need to apply very large forces on the environment and you want that to feel realistic, then you can't just go with skin deformation. You're going to need kinesthetic or force feedback as well. So we can use this type of feedback also for navigation. We can provide guidance. So for example, if we provide skin deformation on multiple fingers, and in this case, it's a holdable device rather than a wearable device, which actually can be more useful for fitting it to different people and allowing them to be able to adjust their grip in a way that maximizes the feedback that they get. So this is a holdable version. And in this case, you can get lots of different degrees of freedom by skin deformation on two fingers and guide people to move in all kinds of different ways. So we've made this transition in my lab from kinesthetic devices now to fingertip wearable haptic devices, but still using mostly traditional robotic techniques. And my lab has been pushing in recent years, going from hard to soft. And that includes origami at the top. So origami haptic devices. I had this dream that I was told that origami devices could be made super small and lightweight. This is the smallest we could make it, and it was bigger than this original device. So either we failed at being origami haptic device designers, or it's just origami devices are not as easy to make as we thought. And then we started looking into 3D printing and having combinations of soft and hard materials. And then, and I'll highlight this on the next slide, fingertip haptic devices that are monolithically 3D printed out of semi-soft materials, where really it's just the thickness of the material determines what part is soft and what part is hard. And it turns out that these are super effective and kind of pretty too. Someone referenced this looking like a diamond ring, so now we've made ones that go on all kinds of other places on the hand like a ring. But they're very effective. In this case, in this much smaller package, we actually now provide 4 degrees of freedom of force feedback, because it turns out the spinny rotation, like the actual rotation of torque on the skin, is important if you want to not drop objects. So it has normal force, shear in 2 directions, and then this torque, this twist degree of freedom as well. And it can do all of these degrees of freedom at a various range of frequencies. So this does have the dirty secret of soft robots, which is that, of course, there are these little tubes here, which are going to the building compressor, but I will address that later in the talk. It is a place where soft robotics kind of cheats, but we really are getting to a point where we can have mobile pneumatic displays. All right, so that was fingertip haptics, but if we want true mobility, uh, occluding the fingers isn't going to work. And there's also this issue that if you want something like augmented reality, where you're combining interaction with real world and virtual objects, if you occlude the fingertips, you can no longer touch these real world objects. All right, so now we have this idea that we'd like to take the haptic devices off the fingertip and put them on other parts of the body. We've done it in lots of different body locations, but the arms are an obvious one. You know, we wear watches, it's very easy to mount. So let's talk about the arms. However, the challenge is that the mechanoreceptors on the skin distributed in these hairy skin locations are not nearly as dense, and they don't have the same types as they do on the fingertips. And then there's this other, maybe more subtle issue that you might not think of immediately, which is that we're very used to exploring the world with our fingertips. We are designed to do active touch, and that allows us to interact with environments. Like if I want to feel the texture on this chair, I don't want to just hold my finger there statically. I want to move back and forth so I can excite the mechanoreceptors in just the right way. So we're used to, and our body is designed to explore the world using the dexterity we've been given in our hands. But now if we're providing haptic feedback on other locations of the body, those are kind of areas of the skin which are designed to receive passive touch and not actively explore the world. So the question is, if we're sort of exploring the virtual world with our fingertips, but we provide feedback in another location of the body, how do people interpret that? And the answer is sometimes okay, but not necessarily great, right? So I'm not going to say, oh yeah, you could feel anything on some other part of your body that you could feel with your fingertips with these haptic displays. That's not true. But we are trying to push the envelope and see what we can do with that. And this is just an example of how when you go from the fingertips toward the trunk of the body, you get worse perception. So I won't get into this, but the idea is, yeah, we have tested people in lots of different locations in the body, and we can actually compare tactile acuity. And we know it gets worse. However, the trade-off is that when you go from the fingertips to the other parts of the body, we have a lot of unused skin real estate. So we can have bigger actuators, heavier actuators, not that we want them to be too heavy, but we can make them bigger and heavier, and we can provide a stronger stimuli. So it turns out that indeed, despite thus moving the feedback off from the fingertips to another part of the body, participants could still identify virtual object properties. Not quite as well as they did when the feedback was on the fingertips, but they can still do it. We also had lots of questions about, if you're providing this feedback to other parts of the body, how should you map it, right? So if you have virtual fingertips interacting with virtual objects like this, you have all kinds of choices about where you provide that feedback. And we didn't want to assume that we were doing it in the right way. For us, this was sort of the assumption of this kind of alignment that would work well, but we thought maybe these other methods would work well as in addition. So here's an example of my student Jasmine having someone do, well, herself, she is doing the task of moving virtual blocks around and providing this haptic feedback. And it turns out the relocated feedback is better than not having haptic feedback at all, which is good. It's not useless. It isn't as good as having it directly applied to the fingertips. And it turns out that all the mappings actually work pretty well. If people are already working to interpret this information, they can interpret it in many different combinations. But if you just ask them on a more of a Likert scale, what did you prefer? They preferred what we call a congruent mapping, where things are sort of spatially aligned, right? So things there's probably, we haven't tested this directly, but it seems like there's more cognitive load associated with mappings that might not be as intuitive. All right, so let's talk a little bit about social touch, because this is not something that's been touched on in the previous couple of talks. Social touch is really important for human health and well-being. And there have been many studies done in the psychology and neuroscience literature showing this. And I'll just give an example of a very common social touch. This is me actually stroking my husband's arm. No students were harmed in the making of this video. And the idea is that, you don't want to have to create a robot finger that draws itself along the skin, right? So the question is, can you use something like a series of individual contact points and rely on haptic illusions and trick the user into feeling a continuous sensation? And the answer is that you can do it, and humans are pretty trickable in this sense. So we've tried all kinds of different fancy devices to do this, like ones that not only touch the skin, but also sort of slide across it. And it turns out this thing on the bottom is not necessary. Just simple indentations in the skin with the right timing, the right pattern, the right spacing, you can make it feel like a continuous stroke. So this works pretty well. And we even showed this. This was interestingly a project that was sponsored by Facebook. It was not Meta at the time, it was Facebook. And they were interested in the idea of haptic emojis with this kind of haptic display. So for social touch, we measured with a capacitive sensor on the arm what social touches were like between pairs of people. We mapped those onto a 2x4 array of, in this case, voice coil motors that we mostly operated very slowly, like near DC rather than as vibrations. And we found that we did a lot of different types of experiments, but here's one example. If you do a valence versus arousal scale and how subjects rated them, the types of social touches that we were given were mapping onto this valence arousal scale, sort of like you would expect, right? That sadness has low valence, like you're kind of sad, and also low. Still relatively heavy. So over the arm, over time, the arm would get tired. And in addition, it was still. So the most recent thing in science robotics next month is we moved to pneumatic actuators combined with maybe variable stiffness knitting in order to still provide the necessary sort of grounding for our knitting can make all kinds of interesting things with fabric. So if you imagine a very simple but when you plate it, it inflates both sides. So in order to actually stimulate the skin and not push away from the skin, and it turned out that by doing this with you can create a really compelling display and overall system. We've been pushing this for social touch for our first paper, but it can be used a lot. Simple 3D. And then when we started doing pneumatics and soft robotics, we were backing ourselves into a corner in terms of an actuation technology that we never get out there. Here we have a system with 8 different stimuli that have exactly a relatively small wearable configuration. Something we need to work on the noise, a bit loud, and there are other techniques that you can use outside of but there's a lot of folks in the soft robotics and soft haptics community portable, and it does move the actuation off from being really localized at the on the trunk. This is a really promising technique. We can get better resolution of noticing where it's occurring with the actuator compared to a vibration. And the idea is that maybe we'll get a little bit closer to the Ready Player One dream, right? With any wearable haptic device, right? Sports feedback from more detailed navigation and guidance. Right now. So what is our goal? So this is actually an unsuccessful one, but we'll try it again. Frosty and Monroe Kennedy, where our dream is to have mobile telepresence that actually don't just worry about the end effect, but worry about the part. And the example that we're going to use is that if you are reaching into the earlier about having the sense of telepresence really being needed so that you get a full understanding of the scenario that you're involved in. The hope is this type of haptic feedback, maybe combined with temperature and other modalities, this sort of multimodality thing really teach distance for wearables. So I'm just going to show you telepresence that will be mobile in the long run. So one is just overall device design questions. This knitting approach that we're doing is one possibility, but just in general, if we want to stay away from just vibrations and we want more perceptible DC or static forces, we need to have large reaction forces. And if those are taken up by the body, there could be clinical challenges for those in the long term. We just don't really know how to stimulate the body with large forces and what kind of impacts that will have in the long term. Another is just perception. There's this interesting balance between the fact that humans' touch sensation is very, very sensitive, but at the same time, it's easily fooled. You can have these haptic illusions, and I feel like we've just barely scratched the surface of understanding those trade-offs. In addition, we often want these devices to work right out of the box, right? You want them to be very intuitive to use. You don't have to learn and adapt to them. On the other hand, there are other scenarios like patient populations who might be very motivated to adapt to certain types of feedback. And so understanding when we need something to work out of the box versus when a professional could use training and it will still be accepted are some open questions. And finally, there are just lots of questions about interaction design. And I'll just throw one example out there. So for augmented reality, when we touch virtual objects and then we go and touch a real object, right now, the way we think about haptics is you see one or the other. But in vision, you can sort of take a real object and make it look different from what it actually is. So one question is, can we do that with haptics? Can we make a real object that you are actually touching feel different from what it actually would feel like? So one example might be brain-computer interfaces, some kind of other stimulation or even peripheral nerve stimulation, but maybe there are other tricks that we can have up our sleeve, other haptic illusions that we can create that make this kind of interaction design more compelling. So hopefully these are some fun food for thought that we can talk about over the meals at the conference. And I want to thank you all and thank my students and sponsors for helping with this work.
Impregnated device or a surface device with flexible silicon. And the other one is in the telepresence activity and looking at the communication fabric. 5G has a latency of about a millisecond. 6G is predicted to be about a microsecond, and 7G is predicted to be near zero latency. What do you need in the telepresence area to enable to use that fabric?
Thanks. Great question. So sort of in the silicon and even MEMS, there's been all kinds of different ways people try to stimulate the skin. The trade-off is usually that if you have a very small displacement, then you need a high frequency in order for it to be perceptible by a person. So I don't really know exactly where that technology is on that scale, and would love to talk to you to find out. But usually we need a high displacement / force in order to be able to do low frequency communications. And so every sort of actuation technology is going to work for a particular range, and it would be great to understand, what that is with today's technologies. The second question, you have to refresh my memory again. Yes. Yeah. So speed of communications and latency. So with kinesthetic haptic feedback, this was a trade-off for decades, right? That you would have instability if you had latency. And then with the type of scenario that Usama Khatib presented, he's saying, oh, you can have a lot of latency, at least as I understand it, as long as you have really good local models and can essentially do autonomy and just send back and forth information. And so I think the answer to your question all depends on, how much can you do what Usama Khatib presented versus how much do you need feedback in order to maintain stability. However, that stability question is really only applicable for kinesthetic devices where there is really a physical closed loop on the system. When you start doing cutaneous displays, where the cutaneous display doesn't create a net force on the arm and therefore move the arm, which then changes the input to your teleoperated device, then you're starting to break that loop, and stability is no longer your limiting factor, but rather human perception. And I think we don't entirely know. It may depend on the type of device, the type of stimulus that you're trying to provide, how much perception would be acceptable, how much delay would be acceptable for human perception.
Thank you, Allison.